Hello everyone, welcome to tutorial 10 of the course. So today we will cover parameter efficient fine tuning with LoRA, so low rank adaptation for fine tuning these large language models. So basically this would cover this paper, basically low rank adaptation of large language models, which the paper basically proposes that so basically what the paper says is that these large language models are very big, like the full fine tuning is not possible. So can we, instead of full fine tuning the whole model, let's say this 175 billion model of GPT-3, what the paper proposes is that they train only a few parameters out of these so that they can reduce the training time and the computational cost while not losing much on the accuracy, much on the metric of the downstream performance, but still they will reduce the number of parameters of the trainable parameters. Let's see. So what the paper proposes is that we propose low rank adaptation or LoRA, which freezes the pre-trained language model weights and inject trainable rank decomposition matrices into each layer of the transformer architecture, greatly reducing the number of parameters for downstream task. Right. So this so the pictorial description would be something like this. This W R D cross D, this is the whole pre-trained weights. Instead of pre-training the whole thing, they introduce two small matrices A of rank R, where in a matrix rank R is the number of independent columns or rows. So they introduce this A matrix and B matrix, and while training this, while fine tuning it, they only train this A and B while freezing the W parameter, that is the whole pre-trained weights of the large model. Now let me show you some results. So yeah. So as you can see, this is Roberta based full fine tuning on multilingual NLI task. So it is 125 million parameters only, so which is very small. But when they use LoRA, low rank adaptation, to a certain rank, they only used 0.3 million parameters. It as you can see, the decrement in the performance is very minute, but the decrement of the trainable parameters is huge. Like similarly for GPT-2 model, so the full fine tuning is 354.92 million, but when they used LoRA, it's 0.35 million. But the blue performance increased, the NIST, as you can see, all the performance have increased, while only training a subset of parameters size, like it is very small compared to this 354.92 million. It is very small, but they still can achieve a bigger number. So the increase, so this little increase or decrease depends upon the task at hand, the downstream task that we are trying to do. But the main point is that we can achieve such performance by only training a very small number of parameters instead of full fine tuning the model for our downstream task. Yeah, so let's move on with our notebook. So we have a small very few in a small introduction to LoRA in a few lines. This is taken again from and we are going to use this PEFT library, parameter efficient fine tuning library, from this is again from Hugging Face, which has various parameter efficient fine tuning methods like LoRA, then quantization, And so there are other PEFT methods as well, like ADA, LoRa, IA3, Llama adapter, LoHa. I mean, please feel free to go ahead and read the documentation of each of these: prefix tuning, P tuning, and so on and so forth. So low rank adaptation of LoRa is a training method that accelerates the training of large language models while consuming less memory. So it adds a pair of decomposition weight matrices called update matrices to the existing weights and train only these new weights. So as we have seen from the paper, so this is the old matrix which is frozen W, this is frozen. We add this A and B matrix which are only trainable. So we add these two trainable matrices which are of rank R to the W matrix, but these are only updated during backpropagation. These are frozen. The W matrix is frozen. So it adds pair of rank decomposition weight matrices called update matrices to existing weights and only trains these newly added weights. So these has couple of advantages, like previous pre-trained model are kept frozen so that the model is not prone to catastrophic forgetting. So as we all know that when we fine tune a model, let us say we fine tune a model on a new task, so there is a high chance that the model will forget what the model was pre-trained on, what was the previous task that the model was good at. So this leads to catastrophic forgetting, where the model completely forgets what the model previously was trained on. Then rank decomposition matrices have significantly fewer parameters than the original model, which means that the trained LoRa weights are easily portable. So these are very small matrices, so we can use, they are very easily portable from one model to another. Now LoRa matrices are added to the attention layers of the original model. So they are added to the attention layer of the original model. So the great memory efficiency allows you to run fine tuning on consumer GPUs like Tesla T4, RTX 3080 or even RTX 2080 Ti, and even GPUs like T4 that are freely available on Google and Colab. So you can, so we will see an example of how we can run a very big model on Tesla T4. So this is the equation that is powering LoRa. So W0 is the base LLM, a base large model, and delta W is the weight that we are trying to add, which is equal to W0 plus BA. So this big W is again decomposed into two small R rank R matrices. Like, so B is D cross R and A is R cross K, where rank of R is less than, very small than minimum of D comma K. So this delta W that we are introducing, that we would fine tune instead. So this W naught is the pre-trained weights which we won't touch, and this delta W is the new matrix that we are introducing, and during backpropagation only this delta W will get updated. So for again for updation, during updation we would break this. So we would do a decomposition of delta W into B and A matrices. So we would do a rank decomposition of this delta W matrix. Now during forward pass, the hidden state will be W, we will multiply X to everything. So just like a normal forward pass. So W naught X is, so this will not get updated, only these delta W and B and A matrices will get updated during backpropagation. So this is the equation that you should keep in mind. Now moving on, we would install transformers, PyTorch, PEFT and datasets. PEFT is the library that I just showed for parameter efficient fine tuning, and datasets is for loading the datasets class, and we have previously installed many times torch and transformers. So moving on, we would import torch transformers like auto model for sec to sec LM, auto tokenizer, training arguments trainer, and from PEFT we would get the get PEFT model function. So let's search get PEFT model. Yeah. So what does this do? Get PEFT model. Get PEFT model. So yeah, so get PEFT model is returns a PEFT model object from a model and config. So as you can see, these are the parameters like model, PEFT config, adapter name, mixed, autocast adapter type, revision, low CPU memory usage. So get PEFT model, then LoRa config, the LoRa config that we are trying to use. So this is the PEFT config. Now let's understand what is the LoRa config. So this is the LoRa config. So LoRa config is basically the low rank adaptation configuration that we would provide the PEFT, our LLM with, like the rank, the LoRa attention rank, that what is the rank, minimum rank that we want to get our matrices into, what are the target modules. So target modules is basically the names of the modules we want the modules to apply the adapter to, right. So this is basically only the modules with specified names will be replaced, right. So there are different types of layers, like if this specified as all linear, then all linear or quantity modules are chosen, excluding the outer layer. So this target modules is basically where the LoRa will be applied. Then exclude modules. So you don't want the LoRa to be applied in this. Then there is a LoRa alpha, the alpha parameter for LoRa scaling, right. Then LoRa dropout, so dropout probability for the LoRa layers only. Now there is fan in bias, use something known as rank stabilized LoRa. So please go into this paper and see, this is more of a stable version of LoRa. Then what should be the initialization of the LoRa weights. So delta W, what we would initialize that delta W weights to. So will it be Gaussian, will it follows the pizza, and so on and so forth. Layers to transform, layer patterns, rank patterns, and layer replication. Use DORA. DORA is another form of LoRa, which is weight decomposed LoRa, you can say. And the task type is basically says the PEFT library what type of task that we want to achieve. So again, from datasets we are doing the load dataset. So we will use the AG news dataset, and take a small subset for this demonstration. So we will take only the first 1000 samples, and we would split the dataset into 80-20 for training and testing. So 800 would go to training and 200 will go to testing. And the model we would use is a T5 small model. Let's take a bigger model to showcase. Let's take T5 base. So it is download. So T5 base, we are getting the auto tokenizer from the model, and the model is getting from auto sec to model for sec to sec LM. So T5, as we have previously seen in the lectures, or you might have seen in the tutorials. So T5 is a sec to sec model which takes input as text and generates output also as text. So it is a sec to sec based task. So we are taking this auto model for sec to sec LM. So this model has been generated. Let's tokenize our dataset. Some preprocess function, mapping is done. Now here we need to define the PEFT config, right. So the PEFT config says, then we will pass the PEFT config in the training arguments. So get PEFT model. So model and peft config. So when we pass this peft config to the model we would attach that delta w to the frozen weights of w, that was the model, the pre-trained LLM weight. So task type is task type dot sec to sec lm. Inference mode is false, rank is 8, LoRA alpha stability factor is 32, and LoRA dropout is 0.1. So let's run it. Now when we apply this get peft model, so model get peft model peft config, when we apply this peft config on the model, and there is also a function which is very cool, print trainable parameters, like. So it prints what is the total params, the trainable params, and so on and so forth. So as you can see, all parameters were something, but trainable parameters are very less. It's 0.39%. So it's very less compared to the number of params that it had. Let's go to large and check. So it is around, the model size is around 3 GB. So T5 base was around 900 MB. So it's quite a big of a model. And if we see how much is what is the parameter size of T5 large? Yeah, let's see the parameter size of T5 large. So T5 large is 770 million parameters. So this is the equation that LoRA is doing. Yeah, so what is the, then there is a question in the paper, like in the ablation section, what is the optimal R that we need to choose? So these are validation accuracy on wiki SQL and multi NLI for different ranks. So these are, they applied LoRA only on the query, this is on the query and the value, and then query, key, value, and also on the output matrix, like after the softmax. So as you can see, for rank 1, then only on query, then on all rank 1. So as you can see, there is not much difference between rank 1 and rank 64. So to our surprise, a small rank as small as 1 suffices for adapting WQ and WV on datasets, while training WQ alone needs a larger R. So we conduct a similar experiment on GPT-2. So this is on similar experiment on GPT-2, and yeah, so as you can see, validation loss on E2E NLG challenge achieved by LoRA. So rank 1 blue, rank 4 achieved the highest score, and so after 16 it got, it got a plateau. So maybe from here you can check that R4 suggesting that the medium has a similar intrinsic rank compared to GPT-3 175 billion. Please go through the paper, super important. Now let's check what is the number of parameters, trainable parameters. So as you can see, so model size has increased, but the number of trainable parameters is only 0.31%. Now let's set the training arguments. So if you want to use weights and biases, go ahead and please do so. For the demonstration, we have set it to disabled. Now training, we are setting the initializing the training arguments, the output DIR, evaluation strategy is epoch, learning rate, per device by train batch size, per device eval batch size, number of epochs set to 1, weight decay and safe strategy is epoch. I set it. Then let's initialize the trainer model. The trainer is we passing in the model, the arguments, the train and the test data set, and we train the model using the trainer API. So what the run name is currently same as output dir, please different. Okay, so we get issue here. Let's check results. So these are previous results. I can just delete the folder and let's try. Okay, so out of memory error. So there is out of memory error that I am getting. So CUDA out of memory, yeah, because so this I have used a large model. Let's use the small model, and for here we set the rank to 8. We can decrease the rank and check how the model performs. Now get the PFT config, set it to the model, and do. Okay, so still getting some out of memory. You are okay, so I think okay, my runtime has been gone up to 3 hours. So please try it at your home. And yeah, so today we saw how we can implement a low rank LoRA, low rank adaptation for large language models, and how we can use the PEFT library from Hugging Face to train this train large language models using LoRa's in very few parameters, and still not be losing out so much on our accuracy. Even in some of the tasks, LoRA outperforms the full fine tuning. So as you can see here, the Roberta full fine tuning on MNLI task or sentence similarity, or sentence similarity or MRPC, the LoRA, which is about 0.8 million only, it outperforms the full fine tuning. So yeah, please feel free to try other ranks, and we will be posting this tutorial on the course website. Thank you.